talk about properties of logarithms in terms of expanding and condensing logarithms. These properties allow us to simplify and solve equations. We will eventually get there. Some properties you already know. You already know that log base anything of 1 is equal to 0, and that's because base anything with a 0 exponent is 1. You also know that log base anything of itself is equal to 1 because anything to the first power remains the same. So these properties are similar and related to our exponential properties. We also have what are called inverse properties. Here I have a log with a base b, and in the argument, a base b with an exponent. The result is just the exponent, because if I take this base equal to this as the exponent, we get the argument. That's a little tough to see, I know. I'll show you a shortcut. Our other inverse property is that if we have an exponential base b and in the exponent a log base b, these cancel each other out and we're left with the argument. And again, if I were to rearrange this and write this in logarithmic form, we would take log base b of this value, and that would equal the exponent, and they are the same. Here's what you want to look at. If you have a log and an exponential with the same base, they basically cancel each other out, and that's what's left. If you have an exponential and a log with the same base, they cancel each other out, and this is what you're left with. We'll get more comfortable with these. Don't stress too much right now. Pause the video and try these. Start again when you're done. You should have gotten log base 4 of 1 is equal to 0. Log base 5 of 5 is equal to 1. Log base 3 of 3 to the 5th, these cancel each other out, and we're left with 5. Exponential base 2 with a log base 2, they cancel each other out, and you're left with 7. We're going to look at some additional properties. They are based on properties of exponents. This property of exponents, we are multiplying like bases. The property or rule is to keep the base and add the exponents. So, based on that, we have a log property, where in the argument, if you have a product, you can expand by adding the exponents. Don't forget, a logarithmic expression is an exponent. It's a different way to write an exponent, so we are adding the exponents. The same property is true the other way. If we have two logarithms with the same base that are added, we can condense by multiplying the arguments. Let's do some examples. If we want to expand, we would expand, since we have x times y, we will end up with two logarithms. They are both base 4. One logarithm for the x, one logarithm for the y, and we add the logarithms. I hope for number 6 you're thinking to yourself, oh, I know that's 2. And you're right, we've done this already, but I want to show you how the properties work. If I rewrote 25 as 5 times 5, and then expanded into two logarithms, since log base 5 of 5 is 1, 1 plus 1 is 2. We already knew that. And in number 7, we have 3 times a times b in the argument, so we will expand to 3 logarithms, all base 3. The logs are added together, 1 for 3, 1 for a, 1 for b, and then there's a little bit of simplifying we can do. Let's condense. 3 logarithms get condensed into a single logarithm, base 2. Since the 3 logarithms are added together, we will multiply the arguments. Log base 2 of cat. And my cat's listening to me record this video right now. Next one. Two logarithms added together, a single logarithm, base 4. Multiply the arguments. 2 times 8 is 16. Oh, hey, we can simplify this. Log base 4 of 16 is 2, because 4 squared is 16. Number 10. Two logarithms. Let's condense into one logarithm by multiplying the arguments. 5 times 2 is 10. This is a log base 10, don't forget. So log base 10 of 10 is equal to 1. Well done. Next property is called a quotient property, and it's based on our exponential property, where if we are dividing like bases, we keep the base and subtract the exponents. That creates for us this log property. If we have a quotient in the argument, we expand with two logarithms with subtraction, because we are subtracting the exponents. The same property works the other way around, where if we have two logarithms subtracted, we can condense them by dividing the arguments. Examples. Number 11, log base 2 of 1/2. We will write a logarithm for the numerator and for the denominator, both base 2. And because of the quotient, we subtract. This allows us to simplify. Log base 2 of 1 is equal to 1. It is not. It's equal to 0. And log base 2 of 2 is equal to 1. Since we were subtracting, 0 minus 1 is -1. Earlier this week, we simplified that by rewriting it as an exponential equation in solving. Here's another way. The properties work as well. Number 12, we're going to start by separating the numerator from denominator. But then when we look at the denominator, there's a product. We have to follow order of operations. When I expand the product, we have to recall that it followed subtraction. The subtraction happened first, and that means we will now have to distribute the subtraction. Notice that anything that was in the denominator is in a separate logarithm following subtraction. That, what I just said, will help with number 13. Anything in a logarithm following subtraction will go in the denominator of the argument as we condense. Then we simplify. 2 times 3 is 6. 4/6 is 2/3. Number 14. 6 will go in the numerator. Following subtraction, the 5 will go in the denominator. That happens first. And then, since the 10 is following addition, it gets multiplied to the fraction, which really puts it in the numerator. 60 divided by 5 is 12. Our last property is called the power property. Because we have this property where we multiply exponents. Remember that a logarithmic expression is also an exponent. If I have an exponential exponent and a logarithmic, which is a type of exponent, we can take this exponent in the argument and write it as a coefficient of the logarithm because it's also an exponent. So we're multiplying exponents. We can also do that backwards. If we have a coefficient on a logarithm, it can be rewritten as an exponent in the argument. Let's practice. We're going to expand. This square root represents an exponent of 1/2. So I do that first, and then I'm going to take that exponent and write it as a coefficient. We consider that fully expanded. There are no more exponents other than the logarithmic version of an exponent. Notice number 16 and 17. They're very similar except for parentheses, and those parentheses will change order of operations. In number 16, I will expand 2 and x to the 5th with addition. Add the exponents. And then I will follow up with this exponent being written as a coefficient and simplifying log base 2 of 2. We consider that fully expanded. For number 17, however, the entire thing, the entire argument, has an exponent of 5. So I'm going to take care of that exponent first by writing it as a coefficient. Then for my next step, I have to realize that when I expand, the expansion, the entire expansion gets multiplied by 5. We can simplify log base 2 of 2 and distribute the 5. So notice the difference parentheses made. Last example's condensing. When we condense, the first thing we will do is write a coefficient as an exponent. Coefficient as an exponent. And then we will simplify those exponents. 5 squared is 25, and an exponent of 1/2 means a square root. Since these logarithms are added, I will condense by multiplying the arguments. And these parentheses are just here for emphasis. They don't have to be there. Last example, write the coefficient as an exponent. Coefficient as an exponent. 8 squared is 64. 2 cubed is 8. And since these logarithms are subtracted, we divide the arguments, and I can simplify. Log of 8, log base 10 of 8. This unit's going to take a little bit more practice, so be patient with it and practice as much as you can. We'll use these properties as we solve equations in the next unit.